So the technique I'm using is off-axis electron holography. And for electron holography, basically we can study the electric field and magnetic field. But in my case, I'm studying the electric field. And talking about electric field, and we care about this electrostatic potential. And the materials for me is latex sphere. This is a very simple geometry sample. But also in this talk, I will talk about some of the other nanoparticles, but also very good shape. I'm now working in a research center, Jülich, and I'm a junior scientist within VRMate. So I work for different projects, but this is my personal scientific topic. And so first, I will introduce the principle of off-axis electron holography, and then I will turn to the study on the polystyrene latex bead, and then I will talk about something on the magnesium oxide and the catalyst. And so what is off-axis electron holography? So this is the image of the machine I use. And so this is basically the same microscope, all the same microscope. This is a TEM microscope. And so this is a gun and the different lens, and this is a stage. The difference I'm using the electron holography is here. So there's a biprism placed above this selected area lens. So this might be difficult to people who are not to understand people who are not working in this area, but more simply we can see this scheme. So in the scheme here, here is a biprism. If we apply some voltage to the biprism, and the beam can be separated. So there are two beams. Here's one. Actually, this is one beam, but the beam is separated. And from this part of the beam and this part of the beam can be interfered after this biprism. If we put our sample here, not in the center, but off axis here, and then this part of the beam pass by the sample, and the face of the beam can change somehow, and then come here, and this part of the beam passing a vacuum, nothing changed. And then later these two parts of the beam can get interference. And then later finally we get this image hologram. If this is a tungsten tip and this is a latex sphere, and if we zoom in this image of this part, we can see this dark and bright fringe. And this dark bright fringe is quite similar as the optical interference. So this is the boundary of the sample. And so in this image, it is consist of the pixel, of course, and each pixel is intensity, and this intensity including the amplitude of the electron beam and the phase of electron beam. So we also acquire the other image, which we call reference hologram. And this reference hologram is including the information of the beam or some background. And when we do the subtraction between this image hologram and the reference hologram, then we can remove the impact from the beam and from the background. And then after the subtraction, we do the Fourier transform. In this Fourier transform, we see three dots. In the center, it is a central band and two side bands. In the central band, the information of the central band is here. It only includes amplitude. But in these two side bands, they have the same information, but in opposite sign. They include the amplitude and the phase. So this part is important part for us. And if we select one of these side band, and then we can further get the complex image. So this part is a complex. So this is also by the visualization, and this is a complex image. So in this image is actually already separate the amplitude and phase. So by the image, this is a amplitude image, and this is a phase image. So the phase image is our purple, and we care about this phase image because in the phase image it can include in the electric potential, and or if your sample is magnetic, it can also include the magnetic potential, magnetic field. And so this is an equiphase contour, and this equiphase contour means how the potential decay, or how the potential change in the sample and in the vacuum. So the distance here, the distance between two fringe is 2 pi divided by 6. So in my case, if we don't have magnetic field and the phase, the relationship between the phase and the potential can be written in this formula. And this potential is related to electric field further. But in this image, this is a very ideal sphere. So for ideal sphere, and if we go back to our very fundamental physics, we can regard this as a point charge. And in the point charge, and is the potential surrounding this point charge should be perfect circle, perfect sphere. But in this image, you might already see that, and this circle surrounding this sphere is not symmetric. So it's not symmetric from left to right because of this tip, the effect of this tip, but also from up to bottom. And this asymmetry from up to bottom is caused by this biprism. And we say it is a effect of perturbed reference wave. So what is a perturbed reference wave? So we go back to see this diagram again. And this is a beam, the parallel beam coming down, and this is a sample. And part of the beam is passing through the sample, and part of the beam is passing through the vacuum. If this part, the vacuum is if this part has nothing and the beam is plane, it is the reference beam. And then after they get interference, and then later we get the information only come from the sample itself. But in this case, if the sample is charged, and if the sample is charged, there will be the potential surrounding the sample in the vacuum. So in this case, this part of the vacuum is not plane anymore. It has some potential in this vacuum. And then finally, this part of the reference wave will give back some potential to the sample. And the effect is just like a charge dipole. Here's a positive. If our sample is a positive charge, it's equal to somewhere another a negative charge, and just like this image. And if our sample is a positive charge and the perturbed reference wave induced by the biprism direction is just like the other negative charge at the same distance respect to this biprism. So that's why this part, the line is denser, but the outer part, the equiphase line is not as dense as here. So this is a principle of off-axis electron holography. And then I'm talking about the electrostatic potential of polystyrene latex bead. And I also changed temperatures. So how do we do this? So again, this equation. And this is a phase, and this is a total potential. What we can get from the experiment is a total phase. And we can get this is a total phase. From this total phase, this phase including both the electron beam induced charge potential and also the mean potential. And at this step, we want to separate these two parts. How do we separate them? So first of all, we use the very fundamental physics. This is a Poisson equation, and using this equation and get some deduction, and we can get the relationship between the charge amount and this phase. So this is a direct relation between the charge amount and the phase from the experiment. And the charge amount is simply equal to the loop integral of gradients of the phase. And after we get to know the charge, and then we can do some simulation. And the simulation is we separate the phase simulation outside the particle and inside the particle. They have different formula. And outside the particle, and we can write the phase in this way. So Q is known, and this is a constant, and this constant, and this is a distance, and then finally we can get the phase contributed by electron beam induced charge. And also same inside this inside the sphere, this is another equation. And from this phase simulation, we know the beam-induced charge contributed phase. But in this equation, we also want to know the mean potential. So this part we know, and this part we know. Now then we can fill the mean potential to this simulation, then we can get the simulation. So this is an experiment, and this is a simulation. And after this, then we can we know this. And so applying that method, and we got this result. First of all, we start from the panel A. The panel A, again, you can see the edge here and here. This is a field of view used by the biased biasing. And so this is what I mentioned, the interference of two parts of beam. And if we zoom in this part and do some phase reconstruction, and we get this image, and from this direction, and we have this phase profile, and on this horizontal direction, we get this this file, or this the horizontal and the vertical is reversed. And you can see here, so this part is on the sample, and this part is on the vacuum. And this is a equiphase. Again, we see this image already many times. And here in this part, if we apply that the equation in the previous page to calculate the charge, if we choose this area to loop integral, and from the top to down this direction, then we can get the cumulative charge. And from here to here, you can see if we start from here, it is a vacuum. That's why it is zero. The charge is zero until it touches the boundary, and it deduces suddenly. And after some distance inside this sample, and it increase. And until it touch another boundary, and it deduce again, and then it keep flight in the vacuum. So the cumulative charge in the whole particle is 158 electron. And for the half, if I select only half of this sphere, is only 92 electron. So here, I want to draw your attention of two parts of this profile. The first part is the middle part. In the middle part, you can see it is a linear increase, but you already see the drop from here. So the linear increasing of the charge profile can indicate the charge distribution. So, and the dropping in the charge profile on the boundary here and here, it indicates the mean potential. So first we check the we want to know if the charge is distributed on the surface or distributed in the volume. So let's try some equations. If it is a surface charge, and this is cumulative charge, if we calculate from the left to right, and the cumulative charge is equal to the charge density times how much the surface we already we are calculating. And the surface area is equal to this, and the surface area is linear to the x. So and also and if we combine these two equations, we know that the cumulative charge is linear to the x. And if it is a volume charge, and the cumulative charge is equal to the volume charge density times how much volume we get. And so the volume has a polynomial relation with the distance. So from this equation, we already actually can judge that the cumulative charge is linear to the distance, but the cumulative charge is a polynomial with the distance. By a more comprehensive way, and we can write the charge on the surface and the charge on the volume in these two equations. If we draw it to make a very straightforward visualization, we see this in linear change is a surface charge, and this curve is a volume charge. In our result, it increases linear, which means that the charge is accumulated on the surface. And then we think about the mean potential. And what is the mean potential? And the definition is the volume average of electrostatic potential with respect to the distant reference vacuum at a zero potential. So maybe this is not so straightforward, but we can simply assume this mean potential as a charge couple on the surface. Again, this is a sphere. If we cut the sphere in the middle, and we get this cross section, and so in this cross section, and if we look at this boundary and zoom in this at the boundary, and the black line is a physical surface of the sample, and the outside is a blue area. This blue area is a negative charge induced by the mean potential. And this inner part here, the inner part, two layers, is a positive charge induced by the mean potential. And it can written in this way. If we plus these three parts, and it is zero, which means that the mean potential induced charge is actually neutral. And so if we go inside the dark bright, it is a beam-induced charge and the polarization charge. And if we draw, samely, we draw a phase line, a cumulative charge line, it is a mean potential charge, induced charge. It from the vacuum, it is zero and z dropping down because the outer surface is negative charged and the inner surface is positive charged, and it increase and dropping down again. So we know in the experiment, the dropping down is coming from the mean potential. Mean potential is actually only a material related parameter. So it doesn't, it has nothing to do with the environment and with the electron beam. So now, so far, and we look back our workflow. So we first start from the experiment phase, and we can get it from the microscope. It is very straightforward. And then we can get the electron beam induced charge. And from the electron induced charge, we can simulate the phase and how much phase is contributed by this electron beam induced charge. And now we want to know the phase contributed by mean potential. And this two part is this two part consists this part, then we can know the mean potential. So again, we do a simulation considering both electron beam induced charge and the mean potential. So this is a charge, our charge sphere, and this is a twin charge. This twin charge can include, can indicate the perturbed reference wave and also the system to make the system neutralized. And if from this phase profile, the solid line come from the experiment, and the dashed line come from the simulation. If we do some simulation and fitting to make this simulation and the experiment consistent with each other. And finally, we get the mean potential of latex, polystyrene latex at room temperature is around 5.5 volt. And we also do some very low temperature experiment down to 5.3 K using liquid helium. So this is a device we used this microscope, and we can connect a tank of liquid helium to the holder, and then the holder can deliver this liquid helium to the sample to decrease the sample temperature very fast. And so at the room temperature, so this is a phase at room temperature, phase at 5K temperature. This is a phase difference. And this is an equiphase contour at different temperatures and phase difference. And from this image, we can see that at room temperature, the density of equiphase at room temperature is lower than that in the low temperature. And if we look at this phase difference inside the materials, we also see some equiphase, which means that the charge is different at different temperature, but also the mean potential change at the temperature. And but using the same method from this image and to do some simulations and calculations, we get to know that at 5K, the mean potential of polystyrene lattice fire is around 6.1 volts. And we also do some different size of latex. This is a larger one, 460 nanometer. The previous one is around 200 nanometer at this one. And we got different temperatures from room temperature down to 70 Kelvin and 29 Kelvin and down to 5 Kelvin. And by the same method, this is tedious. I don't explain more. And we get this image. From this image, this diamond dots is a mean potential we get from different from this method on different samples. They have different size. They are working at different temperatures and maybe using different holder. Some holder can reach to 5K and some holder can only reach to 19K. But we want to select as many as possible data at different temperatures. And this blue line is a fitting of all of this data. And this fitting gave us this equation. And it is almost, the mean potential is almost linear to the temperature, even though it has some parameter at this parabolic item, but is almost linear. And if we substitute the temperature at room temperature and 5K, and we can get the mean potential increase around 6.8%. And we can also see the other line, this diamond dot. This diamond dot is actually the experimental data from diamagnetism. From this, why do we do this? Because this parameter is linear to mean potential, and so if this parameter is linear to the mean potential, and the mean potential is linear to the temperature, and we measured this parameter is linear the temperature, then we can get the relation between this diamagnetism and mean potential. The temperature is somehow like a bridge between all of these parameters. And so this such kind of linear behavior further give us evidence that this almost linear change of mean potential as temperature is correct. And so the next we will talk about some the other application of this electron holography on catalyst. And the first is magnesium oxide. And for the magnesium oxide and the other catalyst, we care about the surface of the oxygen vacancy on the surface. And so measure this oxygen surface. If this oxygen vacancy appears on the surface, and this vacancy can form the color center, and this color center further trap electrons. But how do we measure this? And there are different methods to measure this surface oxygen vacancy. And one method is quantitative hard-diff image. And we know that hard-diff image is a Z contrast image, which means that the contrast of each dot is linear to the elements to this atomic number. If it is a higher atomic number, it has a higher contrast. So same if has a lower contrast, means that the atomic number is lower, or the element amount is less. If the sample is very flat and identical on the thickness, and we can use this method to identify how much how many oxygen vacancy on this surface. So this is one case. And the other method, more straightforward, is STM, the scanning tunneling microscopy. So this is a phosphorus mono vacancy on the indium phosphorus, and this is another case, oxygen vacancy on cerium oxide. And so this oxygen vacancy, this is a electronic level of oxygen vacancy. And well, the vacancy is formed, so some electron can be tracked. So as long as it has some relationship with the electrons, with charge, then we can measure it by by holography. So this is an image from holography at different dose rate on MgO nanocube. This is at 4.1 electron angstrom, the 4.1 dose rate. This is 0.4 dose rate. They have very big difference on the dose rate, and this is the equipotential. So at this moment, I think all of us already know how do we read these images. The denser equipotential phase, the denser equiphase potential equiphase line means that a higher potential, and the looser equiphase line means the less potential. So so we know that at a lower dose rate, and it has a lower charge. At a high dose rate, it has more charge. We did different dose rates on this, shown by this diagram, and the line profile is from here to here, is just far away from the tip, almost along this one direction. So from this image, we can see at a higher dose rate, the slope is higher, and at a lower dose rate, the slope is lower. And if we change, or if we increase the dose rate and decrease the dose rate, and we can almost get the same slope. And so again, we want to know we want to know the electron beam induced charge. So this is the equation. How do we know the electron beam induced charge? This is phase, and this is the other parameters. Then do some fitting, and we know this electron field, electron beam induced charge. And so this image shows at different dose rates how much charge we got. The red symbol means that the dose rate increase, and the blue symbols means the dose rate decrease. We can see very good reversibility here. If we do the linear line of all of this data, and we get this intercept on y-axis, which is around 96 electron, and which means that at 0 dose rate, and without any beam illumination, the nanocube can carry 96 electrons. And this 96 electron without a beam illumination is affects how many oxygen vacancy on the surface. We did more experiments not only on this size, because we want to know where the charge located. So we know how much it, but we don't know where it is. And we did different experiment on different sites. This is another example of 365 nanometer nanocube, as for sure, and this charge become more because of this equiphase line becomes denser. And for in this case, at 0 dose rate, the electron charge is the charge is around 566. And summarize all of this experiment, we got this diagram. The blue diamond dots is from our experiment, and these 3 open dots is from the paper. If we do the linear, we get a curve. This red line is a linear curve. And what is a parameter of this sigma s and sigma v? Sigma s means a charge density on the surface, and this is a charge density in the volume. The charge density, the surface charge density is around 6.7 times 10 to 10, and on the voltage charge density, it looks weird because the error bar is very large, and actually 10 to 14 is a very small value for the volume. So we can deduce that the oxygen vacancy is on the surface, because only this part, only this parameter is meaningful. But how many? And we assume that every oxygen vacancy can trap 2 charge, and then we have half of this charge density, and half of this charge density is oxygen vacancy density. And so this is the image from the from some paper showing the diffusion energy of oxygen. This is a bauxite, this is surface. We can see on the surface, the oxygen vacancy has a lower energy, which means that the oxygen vacancy like to stay on the surface, and which is also consistent with our study. And the last, I will show some very initial result on the platinum on titanium oxide. This is a very common catalyst. And why do we study this? Because for different catalysts, the charge transfer from the matrix to the metal on the surface can introduce a lot of different reactions, and they used at different areas. So since I'm not a catalyst guy, but I'm care about the charge transfer and how much charge we can measure. So the question is that, can we measure such kind of charge using electron holography? And some year ago, there was a science paper. The materials is platinum on titanium oxide, and they measured this the charge on these platinum particles. But their microscope is a very dedicated microscope, and they use a very high accelerating voltage, which is 1.2 megavolt. But generally, so in the most of the lab, we use 300 or 200 kV, so it's very different. Using such a very high, very high voltage, then they can get also high phase accuracy and also very high dose rate. Such high dose rate, actually, you don't know if the charge on the sample is induced by the electron beam or the intrinsic parameter of the sample. And also they use very long capture time. Using very long capture time, the purpose is to increase the phase accurate. But such long capture time is around 2 minutes. It can induce a lot of fluctuation. For example, the sample is shifting or the beam is shifting. this such kind of experimental is very dedicated and is not very suitable for the common experiment. But can we do this in the more general method using electron holography? For example, most of the electron microscope is 300 or 200 kV, and the moderator time it may be 10 seconds or even smaller, 4 seconds, 6 seconds to reduce the fluctuation. Or you can use a low dose, and our dose can be very low. And I use 3, but you can still use a lower on 0.1 less than 1. So to reduce the reaction between the electron beam and your sample. And so this is a very simple example. This work is still ongoing. So there are 2 different samples. This matrix is original titanium oxide, but this one is after laser illumination. And my collaborator already did some work to show that the titanium oxide before laser illumination, it can transfer more charge on the platinum. But after the laser illumination, it has less charge on the platinum. And we measured in the TM. This is a TM bright field image, and this is a titanium oxide. And this small circle I draw indicates the platinum dots, and here from both parts. And then we do holography. So this is the image before illumination. This is the image after illumination. Again, we see this equiphase contour. So this one, we already know that the higher density of equiphase contour means a higher charge, and this one is a less charge. So this work, and you can still in the ongoing, but of course we can still think about how the charge react with the sample, if the electron beam has a very significant impact on the sample. There are a lot of considerations and discussion in the future. But this is only initial work. But from this initial work, we already know that by the electron holography, we can do a lot of application related to charge and related to electrostatic potential. So this is my talk. And to be in conclusion is that for latex bead and using off-axis electron holography, this is a very straightforward technique to study the charge accumulation and the electrostatic potential. And we distinguish the surface charge and mean the potential, and and we also determine that the charge is on the surface, and mean the potential increase as temperature decreasing. So it is nearly linear change. And about the sample on metal oxide, the charge density changes as dose rate, and the charge located at the surface of MgO, and which is related to the oxygen vacancy. And for the other catalyst samples, electron holography is a promising technique to quantify the charge. And I want to thank my collaborators, my colleagues in my institute, Professor Rafa Dunis-Bogoski and Fengshan, Philip, Michelle, Peng Han, and Zhang Yun, and Professor Giulio Pozzi, who helped me a lot on the charge calculation, and Dominic Dennis from Content Zero helped us to do the low temperature experiment, and Professor Feng Wang from DICP Dalian, China, to provide the sample of the catalyst and also the discussion about the catalyst. And thank you for your attention.